Okay, so good morning. Today we study something very interesting. It's called the Chandrasekhar limit, and it sets limits on the masses of white dwarf stars. And so I'll start with something called the Hertzsprung-Russell diagram, which is a map between the luminosity or the brightness of the stars versus the color. And so this I've taken from Wikipedia entry for the HR diagram. So if you want, you can read it. It seems to be a decent entry. And this contains about, it's actually about 23,000 stars, real stars. Okay, so bulk of the stars, are here. Okay, and so these are called the main sequence stars. Okay, and then there is a bunch out here which is not with the main sequence, and the lower one is white dwarf stars. We'll see what these are. I'm just some reason. And then there are many more things, but there's the other stuff. These are called red giants. There's a further classification, but for us, these three are enough. So first, let's discuss the main sequence stars. And Sun is, for instance, an example of our Sun is an example of a main sequence star. And the bulk of the energy which is produced, the sun, that the light rays which come out, radiation that is emitted, comes from hydrogen forming helium, and so that happens in the core. And so this is the main. So they're hydrogen rich. And the red giants, these are ones where the hydrogen in the core is used up. And so it starts using hydrogen in the outer shells of the star. And what that does is that it heats up the star and it expands it. So red giants are really big, and they're also red in color, of course. And so that's the thing. But white dwarf stars are stars for which all the hydrogen is used up. And so the next step in the fusion reaction is helium. So white dwarfs consist mostly of helium, since all the hydrogen okay, so all the hydrogen is used up, and they tend to be dim, because if you look here, they are in the lower end. They are dim. They're fairly dim. Okay. So these are some features of white dwarf stars, and so we need to model these things, and we want to. So our goal is to construct a statistical mechanical model Okay, so so some how will be characteristics of the star that are relevant to us. Okay, the first one is the mass, which we'll use M as the symbol, and this will be equal to, okay, so it contains helium atoms, and the helium has just 2 protons, and of course 2 electrons, and but as we know, the mass of electrons is much smaller than that of a proton, so to a good approximation, it is 2 times mass of the proton times the number of helium atoms. So let's put N. Okay. Then the second thing is that the temperature of the white dwarfs, like most stars, is quite high. So T is around it's around 10 power 7 K. Okay, so at such high temperature, yeah, go ahead.
There is a question by Siddharth. He's asking, why aren't we including the mass of neutrons in the chat?
Helium there has only two does it have a neutron, the helium?
I think 2 protons and 2 neutrons.
2 protons and 2 okay. One second, let me just check. It's also a question of how the fusion occurs. So fusion reaction of hydrogen in a star. Let me check it out. Okay, so it's a reaction where 2 hydrogen atoms combine to form a helium. Okay. So it's just 2.
Okay.
No, maybe I'm wrong. So yeah, so anyway, so actually that's not so important. 2 should become 4 then, right? That's what okay. So we'll leave this as a question mark. It doesn't matter. Okay. All I want really is that it is some known factor times the mass is a known factor times the number of helium atoms. Okay. That's all I actually need. And the second part is the temperature is 10 power 7 Kelvin. So this implies that the helium atoms are ionized. Okay. So what we will have is so the white dwarf will be helium ion, helium nucleus, plus it will contribute 2 electrons. So that's what we have. Okay. So, 2. Okay, n here is not, I will change n here now to make it number of electrons. Okay, so this will, so since there is 2 electron per this thing, the 4 will be taken care of. Okay, now I am fine. Okay, so it will address also Siddharth's question. Okay, so this is what we get, 2 electrons per nucleus. And so what we will do is, we will focus on the n, which is electrons, the n electrons in the star. Okay, so this is what we want to do, and and we will treat it. So for starters, so first, of course, first we will ignore gravity. And treat them as an ideal gas. Okay, so but gravity should not be ignored, so I'll make a comment. The electrons are not in a box. Okay, and but are held in the star through gravitational attraction. Okay, so gravity is actually playing the role of of the box. And so if you assume spherical symmetry, gravity should set the size of the star, and that's what we want to do. And so that's the goal. But before we do that, we'll just act as if there is some so we will act as if we are dealing with an ideal gas of electrons without gravity, and then we'll put gravity into the story. Is this picture clear? Okay. And one more thing. So the radius, so this was 2, is it? The third parameter, whatever, third one is that the electrons are relativistic. Okay, because KBT is fairly large. Okay, mc square, m is the rest is the mass of the electron, and c is of course speed of light. Okay, this you can easy to check. Okay, but I mean you look at it. I've given you what KBT is, 10 power 7 Kelvin, and you can work out what it is, and you can compare it with the. So they have to be relativistic. So in particular, what it says is that the energy moment in dispersion relation is this. And but what we will do is we usually, as usual, will subtract the ground state. We don't worry about creating the electron. So we'll subtract mc square. Of course, we have checked that this in the non-relativistic limit, this goes to p square upon 2n plus order p power 4. Okay, but we cannot make this approximation. We have to use this full formula. Okay, is this point clear? The temperature is very high. The second point, thing is that the radius the radius r is related to the volume v as 4/3 pi r cubed, or r can be written as 3v by 4 pi power 1/3. Okay, so what we have, the two real macroscopic parameters are related to n and the volume of the electron gas. Okay, but here is the interesting thing. The Fermi, so the ground state of the n electrons what does it correspond to? Okay, what do you do at t equal to 0? How do you obtain that? Somebody? Will all the electrons have zero energy? Will all be p equal to 0? Yes or no?
No.
Okay, good, correct. So what happens?
Will they be in the Fermi sphere?
Yeah, okay. So the point is you keep filling it up to some finite energy, so energy or momentum. Okay, so is obtained as follows. So n will be 2, which is the degeneracy times integral, and we'll assume spherical symmetry. Okay, d cubed x d cubed p by h cubed. We have to do this integral so that up to some this thing. So I'll not put the limits now. In the next line I'll put. So d cubed x will give us a 2v by h cubed, but this we can write as 4 pi integral 0 to some momentum p square. Okay, so this will just become n equal to 2v by h cubed into 4/3 pi pf cubed. So pf, we can flip things around. Pf will be 3h cubed by 8 pi v by n, which is little v, power 1/3. So this is called the Fermi momentum. Okay, and and we need some numbers. Okay, so this is what I want. So I'll give some numbers.
Sir, it's n by v.
N by v, thanks. Oh, thank you. Okay, so we need some numbers. Okay, so typical numbers are density, yikes, sorry, I have it in some horrible units. Okay, so from but this is mass density. Okay, from this we know how to go to number density. Okay, and the mass is typical mass is 10 power how much? Sorry, I need my glasses. And we already told you temperature T is of the order of 10^7. Okay. So anyway, exercises compute PF as well as epsilon F, which is okay. So you have to convert this to a number density, etc. But I want to make a claim, okay, which is easy to. I think we computed epsilon F. We got something in MEV, and you can work out what KBT is. The same claim, which should follow, is that KBT upon epsilon F is much less than 1. Okay, what does this mean? So it's kind of bizarre that T in an absolute terms, if you look at 10^7, it looks very big, but when compared to the Fermi surface, Fermi energy, it's much less than 1. Okay, so what does that imply? That we can treat the gas of fermions as if they are at T equal to 0. It's a massive simplification. Is this point clear? Okay. So in other words, all the electrons will be filled up to the Fermi momentum or Fermi energy, and that's it. We don't need to look at anything beyond that. Okay. So now we are ready to compute the internal energy. So our goals will be to compute some properties, some thermodynamic properties. So we want to compute U and P pressure of this gas. Okay. But we had already worked out U and P, right, for the Fermi gas. Can we use those formulae from the past few lectures? I say we cannot. Why?
Because we are working in the relativistic case.
Exactly. Okay. That's because, okay. So we need to compute these first, these, and we will use the canonical ensemble. We won't do the. Okay, so previously what we did was to go to the grand canonical and then do this inversion, etc., like we did in the previous problems. So this is what we need to do. Okay. So what will U be? So we work. It'll be similar to what we wrote here. We had an integral here, right? 2V times the energy, right? So this is like the density of states. So then that would be Is this okay, what I have done? So we just need to do some integrations. So this is a formula, but it's an ugly formula, but okay. And PF is what we wrote here. Okay, PF is a function. Okay, so PF is as determined. Okay. So, and we can get the pressure. We can get the pressure by dV, and so I will now. So we can compute this, but remember, so du by dV is not so simple because this is somewhat messy because PF also depends on V. Do you agree? So there are two. So if I try to mark where V appears, here is one point and here is the other. Okay, so there are two terms which depend on U, and so there will be two contributions. And the first derivative of V is very simple, but the PF fellow is slightly messier. But I mean, not something. It's somewhat messy, is what I said. Doesn't mean it's not good. So this is what we get, and so now I will just try. I will try to define some function. I'll write the formula for U and P, but I'll just write it. I'll write the formula in a moment. So yeah, exercise. Because I don't want to do this computation of taking derivative, etc. Show that P equal to 8 pi by 3h cubed integral 0 to Pf mc square. Okay, so this is so now we have expressions for the pressure and the energy, but now we can let's make it some change of variables. Okay, so P you define it as mc sine hyperbolic phi. Okay. So I guess phi is the rapidity. Okay, so phi. If you remember this from, okay, so you can make this change of variables, and then you get, once you make this change, you get U equal to Okay. So phi f is nothing but p when, value of phi when p equal to pf. Okay. This is u, and let's just define a function phi b by n power 4 c power phi. Don't worry about these factors. And some function b of x, where x, okay, so that's what you get. Similarly, so you can, this is an exercise, but I won't spend too much time working this out. And similarly, the pressure is given by a slightly simpler integral, and this we will call as okay. So you may need to make some change of variables, etc. So so you can actually get explicit formulae for a of x and b of x. So these functions are defined. So just remember that u is some factor times b of x, and p is the same factor times a of x. Okay, sorry, there's a up to a factor of v. So u by v if you wish. Okay, so not very illuminating, but fact is that we can write explicit formula. B of x 8 cubed. Okay. And if you can also, one can rewrite x in terms of the matrix, in terms of the number density, because pf is related to that, right? As follows. Okay. So these are all just for completeness, I'm writing this formula. But what is much more interesting is to ask for how do a of x and b of x behave for small and large arguments. So A of x is equal to 8/5 for large argument, you get this. Okay. And similarly, B of x 12/5 x to the power of 5 minus, okay, I won't write more terms. So one thing, so you can see that if x is small, this is actually the non-relativistic limit because pf will become small. Okay, so small x is the non-relativistic limit. Okay, and then we know that, so you can check that the ratio A is to 2/3. Compare this with, we had this P equal to 2/3 U by V. This was some universal thing we saw for the non-relativistic gas, whether it is Fermi, Bose, or even classical. Okay, so this is just a check but that's just a check of the leading coefficient, 8/5 here and 12/5 here. Okay, only these two will contribute, all others won't. Okay, but for our purposes, we really need the large X behavior in this story. Okay. Okay. So this concludes what we wanted to do about this ideal Fermi gas. So it has some pressure. In the ground state also the pressure is non-zero, and then so what will happen is if you remove walls from a gas, what will happen? The gas will start escaping, right? They'll start leaving. So what you need is to, in this case, to now we need to now to include gravity. Okay, to stabilize the gas, stabilize or confine the gas. Okay, so what we have is gravity is attractive. Okay, and pressure tends to, I shouldn't use the word repulsive, but you understand that that it tends to make the thing grow, and so what we expect is that the volume of the star is such that these two match at equilibrium. Okay, so we need to know what is the gravitational force. We don't know that, so the gravitational force, there are many so there are a few issues in the sense that in the presence of gravity, we do not expect that the star will be homogeneous. There will be some radial dependence, at least. If it's spherical symmetric, there will be some radial dependence on the density, etc. But we'll ignore all those things and we'll just focus on the as if it is it's constant. But that's not. One can do better than what I'm doing. But the gravitational force should be equal to the pressure force. Remember, they're in opposite direction. Okay, so the gravitational force will be G Newton. Okay, so it will be G Newton by the mass square. So it will be proportional to the mass square by the radius square with some alpha, and the pressure will be P times 4 pi r square. We have a formula for pressure. So we just, in some sense, doing some kind of dimensional analysis where alpha is some constant of order 1. Because we are not doing any detailed computation, so alpha will be some thing which one should in principle estimate. We won't. Is this clear? So this will tell you that P is equal to alpha Gn n squared by 4 pi r power 4. Okay, but we already have a formula for P, which is in terms of the number density. Okay, so it is this, right? Where is it? Here. Okay, it's just something times a of x. Let's just call this constant k. Okay, so a priori, I mean, so now this, sorry, it's equal to k times a of x. What this does is that this formula relates mass and radius. Okay, so now so this is some implicit. It's a messy equation, but it's still, so we know right hand side also. So really, it is this combination. Okay, it's okay. All these are known constants, and so we can just so we can compute. We can get a relationship between m and r. But instead of doing that, what we will do is we'll plot a graph. And what is I'm not going to complete the proof, but I'll draw this picture and discuss it. Okay, so this is radius versus mass. Okay, so you get a thing which looks like this, and it comes and touches here at m naught. We'll see what m naught is in a moment. So what it says is that that first thing to notice is that as you reduce so as mass goes down, the radius increases. Okay, and there is a critical mass Okay, ds is 0. What does this mean? What this means is that the gravitation. So at this point, so what is keeping the star from completely collapsing is the pressure from the electron gas. So what this says is that once your mass reaches m naught, that that mass at that mass, you will find that the star can no longer be kept. The electron pressure cannot cancel the gravitational pressure. So at this bottom end, things break down. Okay, and so we need to. You can work out. We can get a formula for m naught, but okay, I will write the formula. So that Fudge parameter alpha comes. Okay. And so the way this formula is obtained is by taking the value of a of x for large this thing and working just to the first two terms. A of x is somewhere here, right? So these two terms, and working with those. Okay, and solving this equation, which I wrote. Okay, this is what you get, and but we don't know alpha, etc. So, but what it says is that, so if you look at this thing, for m greater than m naught, there is no white dwarf. Okay, and a nice calculation shows that so Chandrasekhar m should be less than m naught, which in this thing is I think 1.4 mass of the sun. Okay, so this was his great observation that the white dwarfs should have mass less than or equal to 1.4. But you can ask, what about if there is some star which has a mass greater than that? What will happen? Okay, so that's the obvious question. So electron pressure cannot sustain, so it will continue collapsing. Okay, so it won't go to zero mass, but then what will happen is that it will be so this thing that even the helium, you can think of it, you're better off thinking of it as a gas of neutrons or something like that. So, but neutrons are also fermions. So again, there'll be neutron pressure, and so that's that thing we call that a neutron star. Okay, so that is one possible endpoint. But another endpoint is that there's nothing which can stop it from further collapse, and it just becomes there is a singularity which happens, and that's called a black hole. So for masses greater than Chandrasekhar limit, the endpoint of stellar evolution won't be a white dwarf, but it'll be something else like a neutron star or a black hole. Okay, so this is called the Chandrasekhar limit. And does anybody know how old Chandrasekhar was when he derived this limit? No, he wasn't even a graduate student. He was 19 years old. He was on a ship to England, I guess. Okay, so he was 19 when he actually did this computation. And so for which he got his Nobel Prize when he was a grand old man. It's really amazing. And but those are politics of various for various reasons, and which happens. I mean, at the end of it, scientists are also human beings, but he was a well-respected scientist. Even if he did not win the Nobel Prize, he was a great man. Okay, so I'm done with a discussion on white dwarfs, and next lecture we'll start magnetic properties of ideal gas of Fermi. Okay, so that's all I have to say. So I'll pause for questions.
When will we get neutron star and when will we get black hole? Like,
Oh, those are details. Yeah. So the point here is you have to do one more study and see. So we can do something similar, similar for neutron stars. Now you replace it's a gas of. I think we can do a similar thing, and you will get a bound, which better be. So there is a bound even for there's a mass limit for neutron stars. Okay, so there is another range, but that again they found neutron stars which kind of violate that a little bit. So it's I think it's about 2 times the mass of the sun, I think. So 2 or 2.5. So there is some leeway in that story. And so it's a similar analysis to what we did, except instead of electrons, you have a gas of neutrons, and you draw the same plot. I think you just go ahead and just put these numbers and just see if that works. But neutron star is much more complicated; it has more structure, etc. So yeah, so there is a limit. So this is called this. There is a LIGO. They have been observing a lot of combinations of black holes and this thing. So there is this. There was this gap people were expecting between neutron stars and black holes, but there isn't a gap. And so there are some interesting things in that context, but I don't know that much details. Okay, but you're absolutely right. We can repeat the same process for a neutron star. At least this kind of trivial calculation, but people have gotten more sophisticated. But this kind of trivial calculation will give you some number which is larger than 1.4, something around 2, between 2 and 3, and so on. Any other question?